that the ideal gas law is not a law, but an approximation. It is often a good approximation. We'll talk about when it's a good approximation today.
I'm assuming it's recording already.
So I have it now set automatically to record, so no one
Yes.
has to remind me.
Well, that's why I asked, because I wanted to make sure that it still worked.
I just want to see, I should have some slides. I kind of vaguely remember writing slides for this at one point in my life. Okay, I don't. All right, so we're gonna wing half this lecture, but that's okay. I do it a lot. Okay, I would like to talk today about, we're gonna spend today just talking about Pfiffner, the ideal gas law, and why it's just an approximation, when it's a good approximation, and in particular, I think the focus I want is to explain to you why it breaks to as much detail as I possibly can muster at the point that we are in this class. This is a very conceptual lecture. It's a very interesting one, but it's not like we're not really learning a tool here. I want this more of an analysis lecture of analyzing chemically why Pfiffner is just an approximation. And I want to use the idea again that all Pfiffner is an energy conservation law. Right? All it is a statement of energy conservation between two sources. One is the input heat. Of sample or external environment. Maybe we have a bath that's keeping us at some temperature. And that input heat, any amount of input heat into the system is then immediately used for what we call work, which in this case is just the pressing of the molecules against the walls of the box. Work is just a volume expansion, right? And so we got volume and pressure on the left-hand side, right? So when you see PdV, think this is energy corresponding to the required energy required to maintain the environment of the box. Imagine you have a balloon, for instance, right, which is a flexible material. Probably easier to think about flexible box. PeV is the energy required to maintain that shape and size of that balloon at that volume and pressure. So this is the work required or energy to maintain the environmental conditions. And this is, and so this says that Pfiffner says that every unit, last drop of heat that comes into the system is used exclusively to just press against the walls, 100%. Right? The only thing an ideal gas can do is just move around and hit the walls, right? That remember when we defined an ideal gas, it's massive but point-like, no inelastic collisions. All it can do is just bounce around, hit the walls, and bounce off each other. That requires some energy to do that, to get things moving and hit the walls. And that energy required is Pfiffner, is PV, which is equal to nRT, right? Energy in is converted to energy out. But what if there are other things that the system can do besides PV? Right? What if there's some other sorts of motions and interactions that may add or subtract energy from the heat supplied, right? What if we, for instance, said idea, right? Right. What if the molecules in there have a checklist of the things they need to satisfy to equilibrate? And what we find is that what if the molecules can do other things other than just bounce dumbly? something other than just dumb balls running around, right? So maybe they can stick to each other. Maybe they have repulsions. Maybe they push each other apart. They have an extra pushing force or a pulling force. That's going to change where that heat is going to go, right? You can say that, for instance, if there is an additional use of energy, additional sinks of work, exist in a gas, well, then we would say that Pivner isn't really an applied law, because isn't the correct law, because we're feeding in this much energy, but not all of it is being used for this. It also might be used for something else. So this is no longer an equality anymore. And so there would be maybe additional term, right? We could say that it's actually PV plus some other energy, some other force, or some other source of energy called X equals nRT. Right? And this is the additional motions, or the additional energies, additional potentials. Sink or source. Right? And it could be positive or negative, right? Something could require energy, which means the system needs more energy, but it can also give back energy. Maybe some favorable motion other than PV work that allow the molecules to relax and lose a little bit of energy, so X is negative. Okay? And what we'll find is that this is exactly the case, that we haven't accounted for all the possible uses of this input heat. And that's where we fail, where the ideal gas law fails, because this additional term here becomes comparable or competitive with the PV term. Okay? Means the energy is being used for something else other than just hitting the walls. Now the question is how practical is this? Like, does it really matter? We kind of understand that, if you think about water, for instance, if we had a gas of water, right, waters very clearly like to attract to each other. They form hydrogen bonds. Right? And so hydrogen bonds are an additional motion of the system that isn't PV work, pressing against the walls, that either raises or lowers the energy of the system. In fact, hydrogen bonds are stabilizing and should lower the energy. It actually gives energy back to the system. So that sign would be different. And so we would have to, if we wanted to model water as a proper gas, we would need to consider what the energetic content of those hydrogen bonds are. Because that heat's going to have to be supplied to them to either break them or form them. So let's kind of look, what I'm going to do for the first half of this lecture is look at this idea empirically. Where does this extra term start to become important? In other words, when that term becomes important, when does the gas law fail? When is it no longer a good approximation?
Is that our question of the day?
Sure.
Oh, the screen turned off.
Oops. Something. I think I hit something with my leg. Come on. There we go. Okay, so let's think about what's a good way to measure deviations from ideal gas. Well, what are some things that we can measure in the lab and vary some parameter, the temperature, the pressure, and monitor the response of the system and see how it deviates from our expectation? I'm going to show you two different approaches. So let's consider monitoring, right? So let's define a new variable today, which some of you have already defined for in office hours, but we'll use it today. We're going to see this a lot in this class. Define this new volume we call V bar, which is just very simply the volume of our box divided by the number of moles inside that volume. Okay. This is called the molar volume. And what does this say? Well, this says that at some conditions, the molar volume tells you how much volume you need to fit in moles of material. Right, so let's just think about what these limits look like. What does a large V bar look like? What does a small V bar look like? So as V goes to 0, right? The only way for V to go to 0 is either N gets really, really large or V gets really, really small. Right, so a low molar volume means high density, right? We have a lot of molecules per unit volume. So a small molar volume means means that the density of the system, density is rho, is going to infinity. Right? You're cramming more and more and more molecules into a constant volumes, and vice versa. It goes to 0. Rho goes. Okay, so we'll see that this is an inverse, that molar volume is an inverse of density. So what I want to look at is I can measure the density of my gas. It's not hard, right? I can have a pressure meter, thermometer. I can have a nice beaker of constant size. This is what you're going to do in the experiment next week. And you can measure, the pressure and the volume of that gas and the temperature. And so what we can do is plot PV times V bar, the pressure and volume, as a function of P. How does the volume change as P changes? What I'm going to do is plot on a curve. I'm going to go into the lab and I'm going to vary the pressure of my gas. And I'm going to measure the density of it or the volume of it. Maybe it's a balloon that I'm measuring. The volume's getting bigger or smaller. And I'm going to measure on the y-axis that value of P times the value of the molar volume or the density that I measured. Right? If it were a perfect ideal gas, this is a straight line at constant temperature, right? Because PV is equal to nRT. If T is constant, then PV is the same value everywhere. So I already know what it's going to look like for an ideal gas. Right? Ideal gas, I'm going to have a straight line. Right? At nRT. Value nRT. It turns out that in these units, this is about, it's approximately 22.4 liter atmospheres. I take my units in liters. I take my volume in liters and I measure my pressures in atmospheres. An ideal gas at 300 Kelvin is always 22.4 liters. So again, this is at 298.15 Kelvin. Okay. Every ideal gas you measure at 298 at 1 atmosphere has a volume of 22.4 liters. So that's one of those things you learn in Gen Chem.
Even that sounded familiar.
Yeah, maybe. It's like one of those things that my high school teacher taught me a million years ago, and I just happen to not forget it. So now the question is, all right, this is what we expect, right? So let's go put a real gas in and see how well it agrees. So let's start with the easiest one, right? H2. So I'm gonna plot H2 in green or yellow. And what we see at very, very low pressures, we see very, very good agreement. Right? But as we start to move away, we notice that the volume, screwed up my line. It's supposed to get larger. Stupid. There we go. That's a little better. This is H2. But as a function of pressure, what we find is that in fact, at a given pressure, H2 fills more space than you would expect. Very, very slightly. It's not much. In fact, I have roughly, I think I have roughly the number here. Yeah, 1 atmosphere. So if we say this is 1 atmosphere right here. This deviation for H2. My screen is doing some really stupid right now. This deviation is probably about 0.5% at 1 atmosphere. Okay. What that means is that hydrogen fills about 0.5% more volume than you would expect. It's not much, but it's some. Well, let's put another gas in there. Let's put N2 in there. That's going to be a gas you're going to work on upstairs. Nitrogen is, again, the majority component of air. So the values for nitrogen tend to correspond with those for air as well. Interestingly, when you see this for air as well, that for N2, again, at low pressure, it agrees very well with the ideal gas law. But as pressure gets higher, nitrogen deviates itself, and even more so that hydrogen does. But it's a negative deviation. Nitrogen is more condensed and compact, fills a smaller volume than an ideal gas does. And then we could try one more gas. I'll just put one more in here. Another common gas is CO2. And what you find in CO2 is that it almost virtually never agrees with this, with the ideal gas law. Now, I want to be clear that what the Y scale of this looks like, right? So I don't want to make it seem like it's like going off like crazy, right? So this is about 22.2, and this is about 22.5. Right, so we're not talking about a big deviation, right? We're only talking about like a fraction of a percent deviation, 2%. Right, so CO2 in an atmosphere deviates about 2 or 3%. Is that right? No, it's actually even less than that, right? So this is about 0.1%, and then CO2 deviates by about 1% at an atmosphere. So CO2 is about 1% more compact than an ideal gas is at 1 atmosphere. That's a small error. Right? So when you're doing normal chemistry, like in organic lab and stuff like that, you have to bring in a gas. We don't really care about concentrations, right? It's only 1%. But there are deviations.
Sorry, CO2 and N2 take up less space. H takes more space.
Correct. Correct. Drive that the other way. No, that's correct. Right. A smaller molar volume means a higher density, more compact. Okay, very interesting. Right, we're only in an atmosphere here, right? In an atmosphere, which is what we normally use at, what this says in the ideal gas law is good to about 99 for most gases. Oh, most chemists are fine. Now, in my life, I work at precisions around 10 to the 6, about 6 significant digits. So a 1% deviation is massive. But for organic chemistry, it's fun. We almost never have that kind of precision in labs. But clearly, there's something molecularly dependent about these deviations. Right? H2 is different than N2, which is different than CO2. I want to look at 2 more plots. Similar ideas. I want to look at this at high pressure. I want to see what it looks like as we move towards pressures far greater than a bar. So we start to approach kind of like a liquid, where everything's very condensed. And I want to think about how this varies with temperature as well. Right? These are all fixed. Right? Does these deviations change with temperature? Maybe if we crank the temperature up, it gets worse. Maybe we crank it up, it gets better. Who knows? We'll see. Let's take a peek at that. I'm going to introduce another term that we can measure in lab. And it's very similar to what we just wrote. But this is a really nice diagnostic tool for gases. Call this the compressibility factor. Find what we call Z, the compressibility factor. And Z is just very easy. Z is equal to PV bar over RT. Okay, so it's just taking both sides of the ideal gas law and making a ratio, right? So for an ideal gas law, this has a very easy answer, right? These are PV is equal to RT for gas law for ideal gas. So for ideal gas, Z is always 1. Okay. The nice thing about Z is it allows us to vary P, but also T as well, right? It allows us to think a little bit about the temperature deviations in the gas. Sorry. All right, so let's look at Z as a function of pressure and temperature. And I'm going to be a little, actually, watch this. This is actually really cool. I have a nice tool in here for this. I don't know why I don't use it more. Now I know I don't use it more often. Let's see if that fixes. So like I press you guys can see I'm pressing like the little down arrow there. There should be a little toolbox that pops up. It's popping up on my other screen.
That's so weird.
Yeah, I probably need to restart the program. So I'm not going to do that. I'm just going to suffer through this. So I'm just going to draw it by hand. There is a coordinate system drawer, but I'm not going to. Right. So I'm going to plot here Z versus P. Right. So Z, let's give this some bounds, let's give it some scale. So again, we should always compare versus 1, right? Because that's where an ideal gas is. Right? For an ideal gas, regardless of the pressure, Z is always 1. Okay. And let's vary Z from 0 to 2. The bottom is the origin is 0, and the top is 2. Okay, so what does it mean for Z to be 2? Well, that means that the PV part, the left-hand side, is larger than the right-hand side, right? So that, remember in our first discussion on the first page of our notes here, I'm just going to run back really quickly. Right, X here is varied, right? If X is 0, then PV is equal to RT and Z is 1. But if X is positive, right, Z is going to be larger than 1. And so there's an addition, X is some additional thing that is required for the system to expend, another sink of energy the system's required to use the heat to expend. Right, so that means that if Z is positive, the system wants to, in some sense, energetically wants to push itself away. It wants to make it larger. It wants to expand. Like there's some additional energy that the system needs to do to expand if X is positive. So, and we see here, right, maybe it's not such a surprise, but H2 has this positive deviation. What this means is that the compressibility factor of H2 is also increasing, which means that there's some additional work being done inside the sample in order for the system to equilibrate. There's something pushing the system, the hydrogens away from each other. So when we plot H2's compressibility factor as a function of pressure, we're going to scale this from 1,000. So this is pressure in atmospheres. So we're at very, very large pressures now. What do we see for hydrogen or helium? For helium, we see a positive deviation. Sorry, let me make that more accurate. What does it need to be? It needs to be 1.5 by the time I hit 1,000 psi. It's going to be about right here. Oh, I missed it.
For helium?
Yes, this is going to be for helium or hydrogen. They're very similar to each other. So this is for HE.
Linearly?
It is linear. Interestingly, for helium, it is a linear function. Because it's an atom. It turns out that one of the reasons, it's a complicated reason, but for atoms, this deviation is always linear. For hydrogen, it's a little more subtle. It's low at first, and then it kind of starts to approach the same level for H2. Okay, but He and hydrogen, no matter what you do, no matter what pressure you're at, the deviation is always positive. There's always something pushing the system out. There's some additional repulsion, if you will, pushing the system and stretching the system away. An additional requirement for the system to fulfill. So we can just kind of naively, we can kind of say that these are repulsive gases in some sense. The molecules themselves are repelling against each other. Right? And then contrary, right? If the compressibility factor is less, then that means that when you supply heat, the required energy to maintain equilibrium, the left-hand side, the PE part, is less than you would expect. Meaning that there's some additional energy in the system that the system can use outside of the heat to facilitate equilibrium. And those are associated with attractions. So there's an attractive region as well, and that would be negative. But H2 and HE, they just repel each other. Right? They push out. Now here's an interesting case. What about methane? We haven't considered methane yet. By the way, if I take nitrogen, nitrogen is very similar to H2 in this regard. I'm not going to write it here. In fact, nitrogen is even worse. I'll just go ahead and put it here just to show you. For nitrogen, it deviates even more.
By 1,000, is that 2 or?
Yeah, it doesn't matter. It's qualitative. Okay, but the point is that nitrogen is even more repulsive than H2. And of course, one of the reasons why that is because nitrogen is bigger. This is a bigger molecule. There's more electrons, bigger nuclei. The radii of the electrons are larger. It's a bigger molecule. Some physical size association as well. But what about methane? Right. So let's go to an even more complicated gas. What about methane? Methane has a very, very interesting behavior. Methane at low pressure, relatively low pressure, negatively deviates. And then eventually it comes back around and stabilizes this. And these are all at 298 Kelvin, I should say that. Okay, so methane has a really unique scenario, and again, these aren't perfectly accurate. Use strong the scale roughly. Where methane has 2 limits. There's a region where it's attractive and gas compresses itself. There's a region where it's repulsive and it pushes away. Right, so there's something interesting about methane that's different than the diatomics in the atoms. Now, what about versus temperature? Let's think about methane first. I think methane is probably the most important, interesting of these because it exhibits both behaviors, attractive and repulsive. And it seems to be based on the conditions of the gas.
So now we're doing C versus T?
Yeah, C versus T. And this will be the last plot I'll draw for a while today. I don't want.
At one pressure, at one atmosphere?
No. Okay, so we're gonna do different, okay, so it's still at pressure, it's still Z versus P, but we're gonna have different curves for different temperatures. So it's the same plot again,
Oh, I see.
and we're gonna plot Z for methane at different temperatures.
Oh, I see, I see.
And let's do one. There's our ideal one. So let's start low temperature. So low temperature, this is at 200 Kelvin. We see a very, very, very sharp decrease in Z. And then a slow and relatively linear increase at high pressure. Now, what about 300 Kelvin? How does this change as it warms up? Well, maybe we can think about that, right? If whatever's causing these deviations is molecular in nature, got something to do with the identity of the molecule, then in some sense, the contribution that the molecule brings is not dependent on the temperature. It's intrinsic to the molecule. That's why each molecule has a different curve. But remember what's going on here as we're looking at the balance of heat in to work out. And what's going to happen as we crank the heat up? Well, we're going to pump in more and more and more heat, which is going to make the gas expand. EV is going to increase. But that additional contribution, which is dependent on the molecules, doesn't change very much. Not temperature. Right? Because it only depends on the nature of the molecule. It doesn't temperature independent. So what that means is that the deviation of the energy, that X, becomes proportionally smaller at higher temperature as a fraction of the heat than at low temperature. Right? In some sense, the heat washes out the effects. So at 300 Kelvin, we see even less of a deviation. There's still a small deviation at 300 Kelvin. And interestingly, not only does it not deviate as much, but even at 300, even at high pressure, it doesn't deviate as much.
Do you think it crosses at around the same point or at different points?
Oh, that's a good different points.
Different points.
Different
and
points.
It's at a higher up.
I sure.
Okay.
Don't think too hard about these plots. They're in my notes, by the way, the real ones. I'll post them. And so as we start to increase temperature, let's go to 600 now, the deviations become even smaller. And eventually we could just keep cranking it up. We can only crank up methane so high before it auto ignites and busts or decomposes. So I can't go too high. But you can tell that as temperature increases, the system is starting to idealize. Right? So what are the limits of ideality from this? Where is Z close for all? It's close to 1 for our molecules. Well, it's close to 1 at high temperature, and it's close to 1 at low pressure. So an ideal gas, just by looking at these plots, we can already know where ideal gases are satisfactory approximations. It's where P is small and T is high. In fact, this is a completely general truth. An ideal gas is truly ideal only as P goes to infinity, which means, or sorry, not P goes to infinity. V goes to infinity, or P goes to 0, kind of the same thing, or the temperature goes to infinity. Right? So either the system has to have so much heat that the little molecular dependent energies don't matter anymore, or the space between the molecules is so large that they never see each other anymore. And effectively at large volume or low pressure, each molecule kind of exists in its own shell by itself. There's nothing nearby. So there's nothing to interact with. There's no attractions, no repulsions, because everything is really far away. Right? Kansas versus New York City. Okay. And maybe that's not so surprising. This is one of those things that you maybe learn in Gen Chem, but maybe the more interesting question is why? Why is it that N2 and CH4 and helium, they have these positive deviations, but methane and more complicated molecules can have negative deviations at low pressure? Right. And so I want to explore the chemistry of these interactions and try to understand why we see the deviations that we do.
Is it more about the chemistry or about the physics? Because I was thinking it's more about the physics and like the forces between the atoms.
You're not wrong about that, Anthony. Let's just say that in this class, when I say physics and I say chemistry, I mean the same thing.
Okay.
What is chemistry other than like the chemistry is the low energy physics of electromagnetism. And by low energy, I mean it's low enough energy that the nuclei are bound or apart in photons and electrons. So what I want to show you is I want to tell you kind of a general theory about interactions between molecules. We can use these interactions, this general theory of interactions, to kind of rationalize everything that's going on this page. So let's talk about how molecules and atoms interact with each other. I want to tell you a story first, a physics story, unfortunately, but a very, very interesting physics story. This is a real experiment that was done about 35 years ago, 30 or 35 years. I think it was 1997. The idea is very simple. A research group takes two metal plates. I'll do my best to draw. Two flat aluminum, maybe it's stainless steel plates. I don't know what they are, just two flat plates. Let me clean this up. That does not look like a flat plate. Okay. All right, so we have these two flat, basically rectangular plates of metal. Right, so here's plate one. I'm going to mark it in green. Okay, and this is, I'll explain what the metal is in just a second, right? But let me draw the other one. And there's another metal plate that they place very close to it, parallel to it. Right, so there's another plate here. Let me try to align it perfect, the best I can. That might be the best drawing I've ever done of this. I'm really proud of myself for this one. So I'm just going to kind of color it in red. With two small plates. Plate two. And I'm going to suspend these in the air. They're done using gravity. But what I'm going to do is I'm going to place one fix. I'm going to fix one of the plates to the wall. No, I'm not. No, I'm not. I'm sorry. I'm not. I'm going to connect it to a spring. So imagine on the back side of this plate, there's a spring that's attached to like a paperweight. There's a spring here. This is attached to a spring. And then the second plate I can move back and forth, closer and further away. All right, so I've got some like thick rod sticking out of this plate, right, that I can move back and forth. Right, and I can measure the distance between the two plates. So imagine I take 2 points on the plate and I measure the distance between them. So we'll call the distance between them L. Okay. These plates are as boring metal plates as you can possibly imagine. They can be Teflon if you want. They don't have to be metal. These plates are flat, parallel, and entirely electrically neutral. Right? There's no charge moving through them. There's no voltage being applied. They are the most boring plates you could possibly imagine. In fact, one of the hardest parts about this experiment is to find a material that is boring enough for this experiment to work. Here's the hypothesis. The hypothesis, this was predicted in the 1930s by a physicist named Casimir, who said that if you bring two plates close enough together, completely neutral plates of any material, it doesn't matter what the material, just some sort of electric material, some sort of molecule, some sort of atom, metal, plastic, will be boring. You bring them close enough, they will experience an attractive force between each other. So Casimir predicts that at sufficiently small L, there will be an attractive force between the plates. And how would we measure that attractive force?
With the spring.
Exactly. If plate one is attracted to plate two, it will stretch the spring. Right? So we monitor the length of the spring. We'll call that D for the length of the spring. I really should have flipped L and D here, but that's okay. Right? If we find that if we take the derivative of D with respect to L at constant temperature, if this is greater than 0, meaning that the spring stretches, that means that plate 2 is pulling plate 1 towards it. This implies that there's an attractive force. Right? You're increasing the length of the spring. If it's less than 0, it's repulsive. And if it's equal to 0, it's neutral. Nothing happens. Boring. No attraction. No interaction. Right? Now, you go do this in your room. Take 2 pieces of metal, or pieces of aluminum foil, make them straight as possible. Hang them here, bring them as close as possible together. Assuming you have no wind in the room, that's going to be the real problem. You're not going to see anything. Not surprisingly, nothing. If metal is not magnetized or electrically charged, then they never attract each other. They're just boring old plates. But Casimir says that if you look at the physics carefully enough, there will be an attraction, very, very small attraction. And so people did this experiment. And let me show you the results of it. It's really cool. Now, if you think about these plates as like gases, these are ideal gases, right? They're just boring old metal plates. They have no interesting information. There's no positive charge, negative charge on them. There should be no reason for them to attract. But it turns out they do attract. And let me find a nice picture of the data. Well, this is a slightly more recent experiment. It was done in 2018, it looks like.
I was gonna ask, is 1997 really how like, because I think I know what you're talking about right now. Is that really how late that these
Yeah,
forces?
yeah,
were
the first Casimir force was in 1996 or something. Yeah. It was predicted about 70 years before. Yep. And so this example, so this is the measurement of Casimir force between two spheres. Okay, so it's a little different than two plates, but it's the same idea. And here's the picture. As a function of the separation, the force that's felt by the spheres. Right? The thing is that there is always fluctuations of these things floating because of what's called a hydrodynamic force, which is due to the fact that the system is vibrating a little bit. It's acting like a fluid. Everything's jiggling because there's always little vibrations, right? Nothing's perfectly still. And so what you would effectively see is that as these get closer, the random vibrations of the room and the experiment become a larger fraction of the distance. And so eventually you would see this kind of roll off here, where it looks like there's an attraction between them, but it's just a net vibration of the system. But in fact, when you do this experiment, you don't really see that. Instead, what you see is a linear increasing force as you get closer and closer and closer. There's a new force that appears that's zero at long distances, but the moment you bring these two spheres together to within 1 micron, this is about 500 nanometers, very, very close, there's a new force that appears that's attractive, that pulls it in. Right? These are just boring spheres or parallel plates. They have no positive and negative charges.
So he was right.
He was right. So there's this force. So what Casimir realizes and what is experimentally realized is that, first of all, that the derivative of the spring with respect to the distance between the two is always positive. It's always attractive. And what Casimir concludes from this prediction, and then the experiments validate, is that what all electronic material, meaning atoms and electrons, matter, is attractive to each other, to itself.
Well, there is a no interaction though at some point though, right? If they're
At a long distance, you can't measure it,
okay.
right? But that's a measurement problem, right? If I have two plates at the distance between me and Angie, there's still an attractive force between them, but it's minuscule.
But what about from here?
It's still non-zero, but it's minuscule. The thing is that you can't, that with the measurements that we can do, we can only generate enough force that once it's within about a micron. So that's an instrument measurement problem. That doesn't mean it just turns off. It just means that it decays so rapidly that you can't measure it until things are extremely close to each other. It only becomes macroscopic force. It only becomes a macroscopic force at distances approaching the distance between, not really two atoms. It's much wider than that, but on the order of a couple hundred nanometers. So for instance, if you've ever, I don't know if anyone's ever done this, you guys are young enough, you've probably never even seen one. You ever seen someone try to rip a Yellow Pages book apart? It's very, very hard to do. And one of the reasons why that is because you have, in a Yellow Pages, you have thousands of pieces of paper stacked at very high density on top of each other, with very little gap between. And each of those pages experience this attractive force between them. And when you sum over thousands of pages and effectively thousands of square meters of surface area, you have a macroscopic force, and it's really, really hard to break that force.
I've seen the version where they interlace the pages and like tow cars and stuff.
That's right, exactly, right? You can build a better geometry where it increases the density, the surface contact between pages, which increases the force of attraction. Precise. Right? Again, there's no expectation that two pieces of paper should attract each other. But when you put enough pieces of paper together and close enough distance from each other, they do attract themselves. And it's quite a substantial force. to the point where it takes, world's strongest man to rip it apart.
Oh, is that why sometimes when you have a really heavy book, it's harder to open the pages? Like when you go like this?
Wow, I want to be careful with that because that might have something to do with humidity.
Oh, okay.
Be careful with that. So this is an important point, is everything attracts everything. At some limit, everything attracts everything. Now that's a problem because what did we just see? We saw that some things repel at some pressures. Right, so there must be something else going on as well. But we would expect
Something that's stronger than that.
right. Right. So what we're going to find, and this is a really important point in chemistry as we go on, is that when we talk about things that are, plug my laptop in before it dies. When we talk about things, for instance, that are hydrophilic and hydrophobic, and when we say things don't like water, when we say that something's like organic lipids, right? It's not that water is repulsive, repels the oil. That's not the point. Hydrophobicity is due to a preference. It's that water likes to associate with itself more than it associates with oil. It has a choice. So the water tends to aggregate together and the oil tends to aggregate together. And we'll see that that's entropically favorable and therefore that's what happens. But that doesn't mean that the water molecules are actually repelled from the oil. It's just that the attractions between waters is stronger than the attraction between water and oil. But in fact, they all are attracted, just that some are more attractive than others. So hydrophilicity and hydrophobicity are just a preference. It's not a positive sign and a negative sign of energy. It's just that one's stronger than the other. Everything attracts itself. So what kind of attractions are there? And are there any things that repel? Is there a repulsive force that is something different than this? And in fact, there is. It turns out that there is an additional force that Casimir didn't consider that is actually repulsive. The reason why he didn't think about it, and it doesn't matter here, is because it only applies at the scale of a molecule, at the distance between, like the average distance between two molecules, which is a nanometer at most. This is at hundreds of nanometers, right? So at long distance, things are attractive. And what we're going to see in general, just put this here, is that in general, long distance interactions. All right, and I have to define what long means. Are always attractive. And short distance interactions may be also repulsive. There may be attractive ones and repulsive ones. Can be repulsive. Right. I want to show you these forces in the last. Well, at least we'll get it started, and maybe we can continue into the next class. We have these sense of distances as well. What we're going to see is that in function of distance, some forces are dominant, and then they kind of dissipate and aren't as important when you get close, and other things become more important. So I want to characterize the interactions of molecules into four big classes. Four different kind of unique types of interactions. And again, these can be applied to molecules and atoms. See that some of them don't always apply to atoms, but we can always consider. We're thinking electronic matter as a whole. The first one is what's called the electrostatic interaction. This is the attraction between opposite charges. Or vice versa. or repulsion between like charges. Right. Just classic Coulomb effects, positive, opposite attract. Right, but not everything has a charge, right? For instance, methane doesn't have a charge, and only ions have charges. So you can also have interactions, electrostatic interactions between neutral molecules as well, because molecules have distributions of electrons. They have regions that are negatively charged and regions that have some positive charge. Right, so an example, of course, a good example is what we would call a dipole moment. Right, this includes what we call dipole-dipole interactions.
Is this still part of one?
Yeah, this is a type of electrostatic interaction, dipole-dipole interactions. Right, and a really good example of a dipole-dipole interaction, one of my favorite molecules, acetonitrile. Molecule, you go upstairs and we have liters of it. Okay. This molecule is neutral. It has no net charge, but it does have a asymmetry of where its electrons are, right? Because the CN group is electron withdrawing, right? It's a very polar group. Right, so there's a strong negative, kind of a partial negative charge here, right? And the methyl group, right, is partially positively charged. Right, so we say the molecule has a dipole moment, right? Which is just an arrow that points from the negative charge to the positive charge. Or vice versa, depending on who you ask. Right, so the dipole moment of this molecule, right, lies along the bond and points towards the carbon. Right, this is the dipole. We give dipoles the letter mu, and it's a vector. This is the dipole moment. Right, so let's bring in another molecule, right? Another acetonitrile, right? How would acetonitrile want to associate with itself? Well, the strongest attraction is going to be between a positive and a negative. So the next acetonitrile is going to come in. It's not going to park the nitrogen next to the nitrogen. It's going to park the methyl group next. So a nearby molecule in the gas may be connected to it, right, from tip to tail, as we say. Right? The tail of the dipole connects to the tip of the other dipole. Right? And that's a very attractive force. Right? Acetonitrile has, at low temperature and moderate pressures, an extremely negative deviation in its compressibility. Acetonitrile is a very strongly associating molecule. In fact, acetonitrile is an extremely high boiling point for its size.
Wait,
Go ahead.
There's supposed to be another C next to the.
Oh, that's a typo. Yes, thank you. Sorry. This isn't. Thank you. Acetonitrile boils at like 180. I don't want to say that. 180 Celsius, 150 Celsius, right? It's a very high boiling solvent because in the liquid phase, these dipole-dipole interactions are so strong, it keeps the liquid together. You have to break those dipole-dipole interactions to get the boil. Right? And that's why we have that source of negative deviation in the gas, where Z is less than 1 for acetonitrile, because again, those attractions still exist. You have to break them in order for it to be ideal, where there's no attractions. Something you have to break. And the energy of this, we say that the energy of the dipole-dipole interaction, which is a function of the distance between the two dipoles, call that distance R. So I'll draw it on here, right? R is like, say R is from the tip to the tail. So the energy, this is the dipole energy. Is equal to a bunch of numbers. Some numbers, I'm just going to put it like this, some constants, times the dipole of one molecule squared. So this is mu1, and this is mu2, times the dipole of the other one squared, divided by KBT times r to the 6. So this is a very, very fast decaying thing. If you double the distance between two acetonitriles, the dipole-dipole interaction goes to 2 to the 6. Right, so it decays very, very rapidly. And I forgot a negative sign here. Is there a negative sign? Yes, it's a negative sign. Negative sign. I'll put that in a different color. And the important thing is that it's a negative sign, right? What does a negative sign mean? It means it's attractive. It's an attractive, this is always less than 0, which means attractive. Right? A negative energy, we often say, right? If you think about heat, right? Heat is a positive energy we're feeding in. And what does heat want to do? It wants to blow stuff apart. Right? So a negative energy is something that brings things together. It brings the energy down, right? That means you have P minus X in the numerator, X being a positive number. So the numerator becomes smaller than the denominator in the compressibility factor, and therefore Z drops below 1. Right? So you get a negative deviation because you have an attraction in the system. Right? There's another kind of electrostatic interaction, which is, of course, ions. No, Na plus and Cl minus. That's very, very strong. Oh, sorry. We also have ion-ion. Right, that's Na plus and Cl minus. And that has the U of this goes as minus 1 over r to the third. Okay, so the plus minus attraction is very, very, very strong, but it decays very rapidly as well. So ions are very, very attractive to each other. Right, and so if we have a gas of ions, which is called a plasma, it's not an ideal gas in the least. These ions all talk to each other. They all see each other. If you have a plasma, they're just all communicating. They're all interacting. It's literally the opposite of an ideal gas, because this is a very slowly decaying interaction.
What about of the same? Would it just be upside down? Would it just be the reciprocal or
What do you mean?
positive?
What do you mean?
So what if it was
Yeah, it would just be positive. Yes, they would just be positive. And it's also proportional in the charges too. So I'm just assuming they're both +1 and -1. But if you made this 1 + 2, it would make this twice as strong. I didn't put that there. Doesn't matter. It's linear. Well, added an extra charge doubles it. So very attractive. It decays very slowly. Ions see each other from very, very long distances apart. Okay, so that's number 1. And it's kind of one of those things that you maybe learn in gym. Things are attracted to each other when they have negative and positive charges. But you can do more things with positive charges and dipoles than just bringing them together. You could maybe perhaps bring something in that causes a change in the dipole of something else. Imagine you bring in another object that stretches the dipole of the other molecule. We have a term for this motion. For this second force, it's called induction, which is the let me try to name this as best as I can. It is the energy arising from the change of a dipole in the presence of an electron containing object. Does not have to be another dipole. Let me show you some examples. For instance, if I take acetonitrile, and I mix it with nitrogen. Right? Acetonitrile has a dipole. But nitrogen does not, right? Because the nitrogens cancel each other out. They got the same thing on both sides. No dipole. The dipole of this is 0, right? So this has no dipole-dipole interaction because there's only one dipole. But nitrogen has another property in that when you bring nitrogen into the presence of a dipole, it causes the electrons to shuffle in the nitrogen. And so what happens is the presence of the acetonitrile induces a small dipole in the nitrogen. It causes some of the electrons to move to the left, or it gets attracted to it, or away from it, right? So if this is the negative side, this is the positive side, right? It's going to push the electrons on the left side of the nitrogen towards the right. Right, so that kind of acts as a force on the electrons of the nitrogen and pushes them and induces a dipole in the nitrogen. This is attractive, right? This is where you've created a dipole by basically biasing, by basically saying that, hey, the nitrogen on the left prefers to be more positively charged than on the right, so the nitrogen is going to adjust. We'll bring the electrons over to the right side. And this force is much weaker, but it's still there. U of induction, it's a function of the distance again. And it's proportional to two different values. It would be proportional in this case to the dipole of molecule 1 squared times a new number called the polarizability, which is alpha 2 of the second molecule. We'll look up polarizability in just a second. It's a new number for the system divided by, and this is proportional to, not exactly equal, r to the 6. So what is polarizability? Well, in homework, in the labs, we'll talk a little bit about polarizability in the first rotation. But let's look at Gemini, right? Let's just use a little AI here. And this is a good example, right? Is the ability of an atom or molecule's electron cloud to distort into response to the presence of an external electric field, like a dipole. Forming an induced dipole. And everything is polarizable. Every molecule and every atom has a polarizability. You can cause a helium atom to stretch like a football. You kick the electrons on one side and the positive charge on the other side. You can kind of elongate the atom. Now, helium doesn't like doing this, but you could do it. Helium really doesn't like doing it. But if we can look at the different polarizabilities, it's just a number that you can measure. Let's find Tom. Here's a good example, right? So here's some polarizabilities of bonds. Right? CH is right. H doesn't really have a lot of positive charge in it. It's pretty hard to polarize that, right? So it only polarizes so much when you bring a dipole nearby. But something much more polar like chlorine, right? Or carbon-carbon double bond, or COH, or CNH, right? They're much more polarizable, right? Electrons can move through nitrogen, and nitrogen is much more polarizable than hydrogen, and so on and so on. Right? So it depends on the molecule, but some molecules are more polarizable than others. All right, this is how we get most attractions between molecules that are otherwise have no dipole moment, but in the presence of another one, say like water, creates a dipole, right? For instance, that's why methanol, it's one of the very strong reasons why methanol and ethanol are effectively completely miscible in water. Well, that's also a dipole-dipole interaction, but it's a mix of both. The water is very polarizable and helps to polarize that OH on the alcohol, combines really strongly. That polarizability drops significantly as you start to make the carbon chain longer. Because as you make the carbon chain longer, you've got more CHs and CCs. They're not very polarizable. And so the system becomes that long fatty chain on a long alcohol becomes dominant, and eventually the alcohol no longer is miscible in the water. The same like hexanes, right? Hexanes oil will never mix with water because you can't polarize them. Water doesn't polarize them effectively enough, so it doesn't stabilize the mixture. Meanwhile, methanol and glycine, OHs and H's, acetic acid, formic acid, things that have double bonds, right? They all fall into water, no problem, because not only do they have strong dipoles, but they also are very polarizing. So the water can induce an even stronger force to pull it in. This is why, for instance, chloroform is such an effective solvent, or dichloromethane, is that it has the like hydrophobicity. It doesn't have a very strong dipole-dipole interaction with, say, water. It doesn't have a lot of things, but it does have strong polarizability. So it's a very robust solvent. It can solvate things that are polar, it can solvate things that are non-polar because it's because it's so polarizing. CCl is very, very polarizing. So chloroform, dichloromethane are excellent solvents for that reason. That's why they work so well. Why it was so sad when they banned them. I don't know if you guys know this, but they banned dichloromethane about 2 years ago. You don't use it in lab anymore.
Really? Because we like use it.
Except in very specific situations. It used to be when I was a student, we would just use dichloromethane out on the table. Like I wash my hands with it.
Oh, that's why they always, every time we use it, they're like, be careful, be careful. It's like an extra.
Yes,
What's a carcinogen, right? Isn't that?
it is a very mild carcinogen. Yes. It's also I think it's not really as carcinogenic. I think it's mutagenic. I think it hurts babies.
Yeah, that's the one.
I think
That's
it's a
definitely the
baby
one.
thing.
Like fetus babies or like living babies?
Yeah, like wild pregnant women.
Oh, okay.
Yeah,
Right,
I've
it
definitely
affects
heard that.
children
That's
in
the
the
one.
womb.
That's what, okay. That's why I'm like fetus
I
babies.
think it's para-mutagenic. I don't think it's carcinogenic. If it is, it's very lethal. That's why we used so much of it back in the day, because we knew it wasn't carcinogenic.
No, I think you're right, because I've heard that a little more, the mutagenic.
Oh, that's one of the tricks with solvents is finding something that is, you don't want something too polar, right? You don't want to keep the dipole-dipole interactions in so much that it won't ever take a hydrocarbon. But what you want is something that's robust, that can take some polar stuff, it can take some non-polar stuff. And those are typically these organic polarizable materials, things like chloroform, things like dichloromethane, acetonitrile, dimethylformamide. These are really, really common. Acetic acid, these are really common solvents because they're both polarizable. And they're polarizable and they have strong dipoles. So they give you non-polar and polar. Okay, unfortunately amount of time. So we in some sense, this is kind of where you may be in your understanding of interactions. Well, we'll understand that hydrogen bonds, we'll start next time with hydrogen bond, is a combination of these two. Right? We'll look at why hydrogen bonds are so special. It's just a combination of these two. There's two other forces we haven't considered. What if we put two things that are not polarizable together? It turns out they're also attracted to each other as well. So we'll talk about that next time.
Just want to know what the hell a van der Waals force is.
That is the van der Waals force.
Okay.
Yes, so we'll talk about the van der Waals force next class, and then we'll talk about the repulsive force that none of you have ever heard about. Another force that's new. We'll talk about that next class, guys. And then what we'll do is we'll correct the ideal gas law and do that for a lecture, and then we'll be on to new topics.
I actually know a lot about the repulsive force because it's the reason why I've never had a boyfriend. I have so much. of it.
I guarantee you this repulsive force is not that.
Like, I have a question about the expectations for interpretation. Cause like for the first two, I said that it was dependent on,
That's all I want.
Okay.
Sometimes it just means a sentence.
okay, and then are we still expected to do the Van der Waals problem even though we haven't touched on it in class?
Yeah, it's just an algebra problem. Don't
Okay.
really need to know anything about it.
Okay,
For the bonus, can I put rebar as 20.4 stuff?
No,
Okay.
because that's P times V. Oh, 20. Oh, I see what you want to do. Okay, I see what you're talking about here. I suppose I'm more interested in how do those values vary on, so when you plug in the A and the B,
Mhm.
you're gonna have a function that's a function of temperature and V bar.
Yep.
So fixed temperature to room temperature. What I'm interested in is how much does alpha or kappa deviate from the ideal gas as you change V? So is the V effect very small or is it very large?
So should I leave just VS in terms of V?
Yes, so think about, well, so for instance, maybe you could do this. You could set V to be 1, see what the value is, and look at it at 2 or 10. And see how much those values deviate relative to what you would expect from an ideal gas. So just a compare and contrast, with some plug and chug.
Thank you.
Okay, you're welcome.
Okay, I have two things.
Yes, ma'am.
First of all, is there any chance that, well, are you going to the ACS meeting tomorrow? Okay, so is there any chance that you'll have time before or after the meeting? Well, preferably before, that we can do like a mini office hour, because